Assalamualaikum warahmatullahi wabarakatuh. Today, my group will present about analysis of K-Trust bridge. So, this is our group members. My name is Muhammad Mirza. First, we go to introduction. The K-Trust bridge is an innovative structural design known for its triangular truss arrangement, which efficiently distribute force, minimize stress, and enhance stability. This analysis evaluates its performance, design consideration, and application by examining geometry, material, and construction techniques. Combining theoretical analysis and computational modeling, the study identifies strengths, limitations, and potential optimization to improve efficiency and sustainability, underscoring the K-Trust bridge importance in modern infrastructure and its ability to address current engineering challenges. We go to background case of study. The K-truss bridge, known for its K pattern from diagonal members. The bridge developed in the late 19th century for railway and highway. The benefit is the bridge distributes loads efficiently, reducing stress. This bridge also uses less material and resists buckling well. The bridge handles long spans and heavy loads and combines functionality with aesthetic appeal. The challenge is the bridge requires precise construction and maintenance of ground. Next, we go to the basic theory. What is the K-truss? K-truss is a structural system made of triangle to support load efficiently. The common application is primarily used in bridge structure. The material used is typically made of steel, with timber as an alternative. The key features is hinge connection at all nodes, pin and roller support for stability, and statically determinate system, allowing internal force to be calculated using three equilibrium equations.
Assalamualaikum. My name is Hanif Alif. So for the rail engineering application, number one is rail transport. Railroad bridge number 304 supports freight and passengers, trains connecting industrial and urban areas in Duisburg. Ensure efficient rail operation over the Rhine Canal. Number two is structural efficiency. Through truss design minimizes material use while maximizing the load capacity. Withstand dynamic train load with minimal deflection or vibration. K-truss geometry provides redundancy, redistributing loads during localized failures. Number three is navigation. Offers 6.10 till 6.45 meters of vertical clearance for safe vessel passage. Supports multimodal transport by accommodating both rail and waterway traffic. Number four is durable design. Built with a corrosion-resistant steel to handle environmental stresses. Designed for long service life with low maintenance needs. Number five is heavy load capacity. Handle heavy axle loads typical of freight operation. Support large volumes of good and heavy machinery.
Assalamualaikum, my name is Muhammad Abdul Ihsan. I will explain to you about this calculation. The objective of this calculation is to determine the support reaction and internal forces for each member in the truss structure using equilibrium equation and joint analysis. Okay, the truss structure span is 24 meter and is subjected to uniformly distributed loads, converted into point load for ease of calculation. These loads are applied to nodes A through I. For nodes A and I, the point load is 200 kN per meter multiplied by 1.5 meter equals to 300 kN. For nodes B through H, the point load is 200 kN per meter multiplied by 3 meter equals to 600 kN. These point loads are applied vertical to each node. Taking the moment about point A, we sum the moment of all point loads and set them equal to the reaction at Fy2 times in distance of 24 meter. Solving for Fy2, we get Fy2 equals to 2400 kN. Using total Fy equal to 0, the vertical reaction at Fy1 is also calculated to be 2400 kilonewton. There is no horizontal force, so Fx equal to 0. Next, we are going to calculate the internal forces. Firstly, at joint A, the angle theta is calculated using the geometry of the truss, giving the theta is equal to 53.13 degree. We then apply equilibrium equation to find forces in members P and B. Using the sum of Fy equal to 0, the force in P is negative 26.25 kilonewton. The negative sign shows that the truss is under the compression. Using the sum of Fx is equal to 0, the force in B is 1575 kilonewton. There is no negative sign, so the truss is under the tension. We're moving to the joint B. Using the sum of Fx equal to 0 and the sum of Fy equal to 0, we determine that the force in C is 1575 kilonewton, which is under the tension, and the vertical force at J is 600 kilonewton, also under the tension. Then for joint P, using the sum of Fy equal to 0, we find the force in J is 2100 kilonewton, which is under the tension. Then using the sum of Fx equal to 0, the force in Q is negative 1575 kilonewton. That shows the truss is under the compression. Lastly, at joint J, using trigonometry, the angle for beta is 33.69 degree. From the sum of Fy equal to 0, the force in C is 1352 kilonewton, 0.10 kilonewton, which is tension, and the force in Q is also, but in negative, 1352.10 kilonewton, which is under the compression. In this analysis, we determine all the internal forces in the truss members and verify the equilibrium of the system. The results indicate whether each member is under the tension or under the compression, which is essential for designing safe and efficient structure. That's all from me. Thank you.
Next, for the discussion, why we use the K-truss design. We use K-truss design because the shorter vertical members can resist buckling under compression more effectively. This enhances the bridge stability and load carrying capacity. Next is static equilibrium principle. The railroad bridge number 304, like all well-designed truss bridge, follow this core principle to remain stable under train loads, wind, and environmental forces. Sum of horizontal forces is x-axis is the sum of Fx equal to 0. Sum of vertical forces y-axis, sum of force of y equals to 0, and sum of the moment is 0. So the method for calculating truss forces, there are two methods to calculate the forces. One of them is method of joint. Analyze forces at each joint. Apply equilibrium equation to solve for unknown forces in connected truss member. Number 2 is using the method of section. Focus on specific members by cutting through the truss. Use the free body diagram, one of the section, to calculate force efficiently. So, for the conclusion, truss bridge like railroad bridge number 304 exemplify an exceptional balance of material efficiency, strength, and stability, making them ideal for heavy-duty application, such as rail transport. Their triangular geometry efficiently transfers load through axial forces, minimizing bending and enabling optimal material usage. This allows for long spans the ability to support significant loads and reduce construction costs without compromising the safety. Still dominate the truss bridge construction due to excellent strength to weight ratio, durability, and affordability for large, heavy structure. However, modern innovations are introducing alternative materials like aluminium for lightweight needs and FRPS for corrosion resistant and extreme environmental conditions. The efficient arrangement of axial members in truss bridge ensure optimal force distribution, minimizing material waste and providing an economical and sustainable design. By applying the principle of static equilibrium, this bridge maintains stability under both static and dynamic loads. Bridges like the Duisburg Railway Bridge showcase how truss design can adapt to increased traffic demands while ensuring longevity and minimal maintenance. The combination of innovative materials and efficient design principles secure your role in meeting future infrastructure challenge, including sustainability and growing load demands.